right. Excuse me. All right, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this weather and it's a bright morning, and just pray that you be with us, help us to glorify you what we do, and understand a little bit more about the Schmidt algorithm and orthogonal matrices. Lord, in the name of my brother Jesus, amen. All right, so the problem that we face today is the problem of taking a given set and trying to replace it with a orthogonal set, right? Now, it's probably good for me to just explain a little bit more about the utility of a orthogonal set, or better yet, an orthonormal set. So, let's see here. So, theorem, if we have beta is v1, v2, vn, and vi dot vj is equal to Kronecker delta ij, then of course if x is equal to the sum I equals 1 to n of ci vi, then ci is simply obtained by x dot vi. That is, the coordinate vector of x with respect to the beta basis is simply equal to like x dot v1, x dot v2, x dot vn. All right, so that's something that I probably should mention in here and emphasize from time to time. If we have an orthonormal basis, we can calculate the components with respect to that basis. Simply by taking the dot product. So, like, the most probably familiar example of this is simply the case of the standard basis, right? To calculate the components of a vector with respect to the standard basis, if I have x is equal to 1, 2, 3, 4, of course, this is what? This is, x dot e1, x dot e2, x dot e3, x dot e4. I just decided something I'm doing next semester. Anyway, or maybe this semester. Okay, so, but not today yet. So my point to you is, of course, this is kind of a dumb case because the standard basis, the vector is its own coordinate vector, right? But you can see this in action, right? To find the first component, take the dot product of v1, right? And so forth and so on. The proof of the theorem is probably worth doing. It's like a line. If we have x is equal to the sum I equals 1 to n of ci vi, then what happens if we calculate x dot vj? Well, x dot vj is equal to, the sum I equals 1 to n of ci vi dot vj, where I've just used, by the way, the fact that the dot product is additive, right? We can bring a sum into the dot product or out of the dot product and pull scalars out. I'm using that. It's kind of hidden in the summation notation, but it's there. And but you see, we're assuming that this basis beta is orthonormal, right? This dot product relation says that they're perpendicular if they're different, and it says the length of each one is 1, right? Because the dot product of the vector with itself is 1. Just a reminder, this is the Kronecker delta, right? The Kronecker delta is equal to 1 if I is equal to j, if it's equal to 0 otherwise. It's the natural enemy of the finite sum, just leaves you with Cj. Therefore, Cj is equal to x dot Vj for all j. And there we go. So if I give you an orthonormal basis and I give you a vector, I say calculate the coordinates of it, this is easy. You just do this, all right? This is very much related to the fact that, in fact, it's pretty much the same theorem as the fact that this is also equal to what? This is also equal to beta transpose times x. That's just a way of writing all those dot products at once. Because when you multiply that matrix out, what you're looking at is a stack of dot products with the basis. Okay, anyway. Now that's great. But there's more I should talk to you guys about. Projections. All right. So, like first order of business, if I have a vector, let's say A, and I have another vector, let me make this B actually, vector B, and I have a vector down here of A, right? I can decompose the vector B into two pieces, you see. I can break it into two pieces. I can break B up into a vector which is parallel to A, right? The part which is parallel to A, which is just like this piece, right? That's called the projection into the A direction of B. All right? I can do that. And I can also take another piece and make it perpendicular to that, like this, and I call that the orthogonal projection of B in the A direction. All right? What are the formulas for this? Well, the formula for the projection to A of B is simply equal to, what we do is we take B and we take the dot product with the unit vector in the A direction and we multiply it by A hat. This gives me a vector whose length is as long as it needs to be, namely B dot A hat. All right? And its direction is in the same direction as A, because remember, A can be written as the magnitude of A times A hat, right? The unit vector in the A direction is defined, you may remember, as the vector A divided by its magnitude. Right? This is the normalization of A. Now, of course, I'm assuming A is not equal to 0. If A is equal to 0, well, I have no business doing this. Yeah? What's the formula for the orth? Well, by construction, we want the projection of A, B onto the A direction, plus the orthogonal projection of A into the B direction. We want the sum of these two things to be B. All right? They have to build back to the vector B, so you can see it's inescapable what the formula has to be for orth. What is it? Yeah, exactly. B minus the projection, which I'll write as B dot A hat, A hat. This vector will be perpendicular to the projection of A, and also A itself. All right. If you're perpendicular to a vector which is a multiple of A hat, you're perpendicular to any scalar multiple of that. So, you know, this gives us a very nice way of solving problems. Like, for example, if you had a problem where you're trying to find, you know, the distance from a point to a line in 3 dimensions, you could use this to figure that out, right? Like, I'm not going to do this example in class, but I'm just going to like sketch the idea. You know, if I had, for example, a line that went from 1, 2, 3 over here to 5, 17, 9, right? And supposing that I pick a point that's not on the line, you know, like wherever here, I don't know, 6, 100, 0. There, I'm pretty sure it's not on the line. I really don't know where it is relative to that, but the point is, I could, you know what the closest, there has to be a direction vector to this line, right? So if I call this, let's say P, and I call this, let's say Q, right? Then if we let A equal to Q minus P, this gives a direction vector to line, right? Call this line L, right? And so I could picture A like this, yeah? You know? And then I could picture another vector B like this, right? And B would be equal to what? I'm going to call this R. It would be R minus P, right? And what would where would the closest point on the line be? It's a weird color. So you draw the perpendicular bisector to the line, right? I was attempting a perpendicular bisector, right? But this vector right here, I think I chose my A and my B backwards maybe to my previous setup. That's no big deal. This vector right here would be projection in the A direction. Well, I guess it's, yeah, projection in the A direction of B. I guess that's what I did. Oh, yeah. And so the point which I'm interested in, the closest point to R on this line, this guy right here, right? What would that be? This point, which I'll call Bob. So Bob would be equal to, like, we could do vector addition, right? Starting with the point P plus what? Plus the projection onto the A direction of the B vector. And that should give me that point right there, which would be the closest point, as it turns out. I'm just claiming it's intuitively obvious at the moment that that's the closest point, because these are, by the way, perpendicular. This is perpendicular. And like, so, well, anyway, we'll talk more about closest point stuff on Friday, so let me not do that now. So this is what projection does for you as an example, but there's more than this. Like, let me talk also about, like, theorem. If we have W is equal to the span of, let's say, beta sub W, all right, where beta sub W is equal to, let's say, like W1, W2, all W's, WK, orthonormal, all right? So what I have in mind here is a subspace. Okay. This is a very good classroom if we could just ignore the gazebo upstairs. Like I really like this classroom, modulo the elephants walking on the roof from time to time. Okay, so this, I'm thinking of this is a subspace of Rn, all right? So a generalization, here I'm talking about the projection of a vector onto a line, all right? But we can also talk about the projection onto the W subspace of a point. All right? And the formula for this is simply as follows. You take the sum, let's say I equals 1 to k of x dot wi, This gives you the part of the vector x which lies in the plane W, or the subspace W. And you can also talk about orth as x minus the projection. This will be an element of W perp. All right? So like a picture schematically could be something like All right. So here's x1, x2, x3, all the way out through xn, all right? This is a somewhat heuristic picture. It's an n-dimensional picture, yeah? And what I'm telling you is if we take a vector in n dimensions, we can visualize it as, of course, a vector from the origin, right? And I'm telling you that that vector can be decomposed into two pieces. Basically, we just drop a perpendicular line down here to this point, all right? And there's this vector right here, which is the projection onto the W space of x. And the other piece is this piece, the orthogonal onto the W space of x. And these guys, in fact, are perpendicular. All right. So if we had an orthonormal basis, we could build this projection onto a space, all right, like this. Like the proof that orth and proj are perpendicular maybe is worth doing for a second here. What happens if we calculate the dot product of the projection and the orthogonal projection onto W of x? We've got what? The sum I equals 1 to n of x dot wi, that's my projection, and I'm supposed to take the dot product of that with x minus that. I'll do the sum over j this time. So this gives us the sum over I equals 1 to n of x dot wi times wi dot x minus the sum over I and j of x dot wi times x dot wj, and then we end up with wi dot wj. So all I did was just distribute. There's two things in the orth. As we calculate the dot product with those two things, I rearranged them, pulled out the sum in the second term. But look at what happened. We have like this term to start with, right, which is just x dot wi squared summed over I, right? And on the flip side, that just comes from taking the dot product of x with wi, right? This wi with that x is that one, yeah? This term is coming from this dot that. All right. So notice that this is Kronecker delta ij by assumption, because we're working with an orthonormal basis for W. So we have the same thing, because the sum over j collapses, and we just have sum over I of w dot xi squared. So this is equal to 0. That proves that I'm justified in putting my little right angle thing there, right? They are indeed perpendicular vectors, right? Which means what? We can go back to the orthogonality, like the Pythagorean theorem we did the other day, and we can say, aha! So the length of x squared is equal to the length of projection of x onto w of x squared plus the length into the orthogonal projection onto w of x squared. You know, by the way. Right. So I hope I've convinced you, if you needed convincing, that having orthonormality of a set is very, very helpful, because we can build these formulas with it. All right, so how do we actually make a set orthonormal then? So this is the Graham Schmidt, I can't spell, Schmidt algorithm. There we go. Given a linearly independent, that's important, set, let's say S, equal to, let us begin with, say, V1, V2, Vk, all right, which is a subset of Rn for us, okay? This concept generalizes, though, to abstract vector spaces, if we knew what that was, what those were, all right? We will learn what an abstract vector space is in, like, the final day of class. I'll do, like, one day where we do it, or maybe two. Anyway, we'll see. You will not be tested on it that deeply, if at all. Anyway, so this is a linearly independent set. So the Graham-Schmidt algorithm says to create an orthogonal set, let's call it S prime, V1 prime, V2 prime, Vk prime, proceed as follows. So step number one, this one's pretty easy. V1 prime is equal to V1. All right, this one no one should get hung up on. All right, good. Step number two, V2 prime is equal to V2 minus, here we go, V1 dot V2. I probably should put a V1 prime here, divided by V1 prime dot V1 prime. Now, technically, I don't need the primes, right? Because V1 prime is equal to V1, so it wouldn't hurt us here, but it will hurt us in the future steps to not put primes there. I'm not done yet. This is just a number, and then I put V1 prime there. Yeah. What is this? I guess it might have helped if I had finished writing the formula for projection. See, this projection is actually B dot A divided by A dot A times A, right? That's the formula for projection. I'll write it over here. So, like, by the way, the formula for the projection onto the V1 prime direction of V2 would be equal to V2 dot V1 prime over V1 prime dot V1 prime times V1 prime. Because, like, V1 prime hat is V1 prime divided by the length of V1 prime. Yeah. So, like, when you unwrap the projection, you're actually dividing by the dot product of the vector in itself. Now, those terms weren't apparent in the theorems that I just wrote down. Why? I assumed orthonormal sets, length 1. So the division by the dot product of the vector with itself didn't appear because those were 1. But we're not given that this is length 1, and we really, here's the thing, guys. I don't think orthonormalizing as you go is a good practice, because it brings in square roots, which are annoying. So if you don't normalize as you go, you'll have, I think, relatively in the big scheme of things, less square roots to deal with in the calculation. It is a simple matter, after we're done constructing the orthogonal set, to go back and to normalize the thing all at once. You just go through and divide by the length, divide by the length, divide by the length to create the orthonormal set. But this right here, guys, this vector v2 prime is perpendicular to v1 prime. See that? Well, if we see, whether you see it or not, trust me when I tell you that v1 prime dot v2 prime is equal to 0. How do I know that I'm not dividing by 0 there? It's a linearly independent set. Can we have 0 in a linearly independent set? The answer is no, right? No. So check out what this formula does. What we're doing, all right, understand the formula. What we're doing is we're subtracting off the projections of v3 into the directions given by v1 prime and v2 prime. We're subtracting off the part of v3 which lies in the 1 prime, v1 prime, and v2 prime directions. All we're left with then is the part of v3 which doesn't lie in the direction of v1 prime and v2 prime. In particular, this is going to give us v1 prime dot v3 prime equal to 0, and v2 prime dot v3 prime equals to 0. That is a consequence of that formula, right? So if we can do it once, we can do it twice, we can do it k times, right? So you keep going in this way, dot, dot, dot. And then the kth step, I suppose, here, vk prime is going to be vk minus, well, I'm tired of writing. So the sum, I equals 1 to k minus 1, I suppose, of vi prime dot vk, no prime, divided by vi prime dot vi prime, all times, of course, vi prime, right? And this will make vk prime an element of v1 prime, v2 prime, da da da, vk minus 1 prime, what? What do we put here in order to communicate this vector is perpendicular to this list? What's our notation? Remember, we do a perp. The perp of a set of vectors is the set of all vectors orthogonal to this given set. By construction, vk prime is orthogonal to v1 through vk minus 1 prime. All right? Now, there's a lot of things I come to in mathematics where I feel like there's no way I would have ever thought of it. This isn't one of those. Like, I feel like if you understand what projection is and you start tinkering, you can derive this method for yourself. I did in the notes, if you look through like successive orthogonalizations of the vector. So I derived this formula from like successive applications of the orth operator. I don't think that's a good way to calculate, but it was helpful for me to understand, right? And if that helps you in the notes, great. If it doesn't matter. You just need to know this formula and be able to apply it to sets of vectors. All right, let's do it to a particular set of vectors. If I can find a particular set of vectors. All right. Let me pick I'm going to pick an even problem from no, I'm going to pick an odd problem from the book. Well, I'm torn. All right, let's. I think I know which one. So working with a basis of vectors, which are like pairwise perpendicular, is super nice because it's what we're most used to, and the formulas are most nice. If we have to work with a basis where the vectors are not perpendicular, like that happens. Sometimes it's inevitable, right? There's lots of places where the eigenbasis for a matrix might not be orthogonal, and that's fine because it's still an eigenbasis, which means that you're, entitled to all the rights and privileges thereof, which are considerable. All right. So I'm not saying you always have to use an orthonormal basis, but man, if you can, everything we know about length and perpendicularity transfers to such a basis. It's almost as if an orthonormal basis is the standard basis with just wrong notation. So it's incredibly useful in terms of intuition and things. Okay, so here's an example we can do. Let's look at, am I on 3? Okay. Let's try to run the Gram-Schmidt algorithm on, I'll let S equal to, and I'll be vertical here for a change. I hope we can finish this in the time of class. 2. Oh, wait a minute. What am I doing? There's an M by this problem. This is dumb. Let's scale it back a bit here. 3. My apologies if I'm doing one of your homework problems. 1 minus 1, it's possible. 3 minus 5. 1 5 minus 7. 1 1 minus 2 8. All right, so I want to look at these 3 different vectors. So just as a point of labeling, let me just double check that 3. Usually I make the mistake in copying the problem down, right? I mean, it wouldn't really be a mistake per se, but we won't be able to check our answer if I don't copy it down right, All right, so have any of you guys tried to run the Gram-Schmidt algorithm with ChatGPT? I haven't either. That is allowed in this class. Even if you're an honor student, I am officially giving you permission to use ChatGPT to try to do this, to check your work. But be forewarned, ChatGPT does say stuff like 3 is greater than 4. So it has to be reined in. It's, not always smart. But anyway, so this is, well, my larger point is that there's a lot of calculation here. So it would be wise to find a website you can kind of like bounce ideas off of, right? But here's V1, here's V2, here's V3. All right. So let's run the Gram-Schmidt algorithm on this, see what it is. So first of all, V1 prime, that's easy, yeah? And I'm going to write it like this, just to save board space, if that's okay with you guys. Now V2 prime is, I'm going to write it symbolically, it's V2 minus V1 prime dot V2 divided by V1 prime dot V1 prime V1 prime, right? I think if you look at this algorithm, it's worth our time to carefully calculate V1 prime dot V1 prime once we found it, right? We're going to need that number later anyway. What is V1 prime dot V1 prime? 9 plus 1 plus 1 plus 9. Also known as 20. All right? I see fractions. Fractions are upon us. So minus 5, 1, 5, minus 7, minus... Now what is V1 prime dot V2? So I've got what? I'm sorry if it's going to get messy here, but rather than doing it in my head, I'm going to do it up here. V1 prime dot V2 is minus 15 plus 1 minus 5. If you see me make a mistake, you stop me, please. Minus 21. All right. You might feel like I'm being overly concerned about making a mistake on something that's so simple. I speak from life experience. This algorithm is hard to implement because it's got just enough arithmetic for you to get it wrong. Oh, I like that. I think that's, I thought it was 0, but it's not, is it? Is that 0? What is that? Negative 40? All right. So minus 40. And, oh, well, hey, that's convenient, 20. I like that a lot. And V1 prime was, oh yeah, 3, 1, minus 1, 3. You got lots of opportunities for mistakes here, right? Because it's such an easy thing to copy the wrong vector into the wrong spot if you're not being careful. It's important for us to check our work as we go, right? Once I'm done with this arithmetic, we should check that the dot product of V2 prime and V1 prime is 0. If we did it right, that'll happen. If we didn't, it won't. So what we got here is minus 5, 1, 5, minus 7. And minus minus is a plus, and that's a 2. So we get plus 6, 2, minus 2, 6. I believe that works out to 1, 3, 3, minus 1. All right, so if I take the dot product of this guy, my alleged V2 prime, I get 3 plus 3 is 6, minus 3 is 3, minus 3 is 0. Hooray, V2 prime is indeed this. All right, so we know we're going to need, it won't be a minute, we're going to need V2 prime dot V2 prime. What's that equal to? 1 plus 9 plus 9 plus 1, also known as 20, right? And we're also going to need to calculate what is V3 dot V1 prime and what is V3 dot V2 prime. Let's just calculate those and get those in front of us before we need them. All right, so let's see, your V3 dot V1 prime is what? It's 3 plus 3. Wait a minute. Hold on. 3 plus 1, right? 3 plus 1. Minus a minus is plus 2 plus 24. Which is 30. You know, this is a nice example. This is why I'm so sad that we can't use lay anymore. Mostly because I refuse to make you guys buy the $200 most recent edition of it. And the bookstore says it can't find the plentiful $10 edition. So whatever. I think Dr. Majerick is still using it. Well, I shouldn't say more about that. Let's see, here's a V3, V2 prime. Where are we? All right, so V3, V2 prime, I got my dot product is what? 1. Where was I? V3, V2 prime, all right, so plus 3 minus 6. So one thing you should be thinking about is what's like a good calculational etiquette that could make this easier on yourself, like an organization of how you write it that would make life easier, you know? All right, so 10. All right. Great. So what's my V3 prime then? Is it 10 or minus 10? Oh, minus 10. Thank you. That'll come up in a minute. 10 minus 10. Very good. So V3 prime, remember, is V3 minus V3 dot V1 prime over V1 prime dot V1 prime minus V3 dot V2 prime over V2 prime dot V2 prime. That's it, right? So we've got all these numbers. My V3 was Tell you what, I'm going to write it vertically this time just to be different. And also because I'm going to run out of space if I go horizontal. 1, 1, minus 2, 8, minus, all right. See, I have, this is nonsense. You can't add numbers to vectors, can you? No, what am I missing? V1 prime, V2 prime, right? So this fraction here, V3 dot V1 prime was 30. V1 prime dot V1 prime is still 20. V1 prime was 3, 1, minus 1, 3. All right, and then minus V3 dot V2 prime was minus 10. And V2 prime dot V2 prime is 20. Looks like the fractions are upon us. 1, 1, minus 2. Usually fractions happen. It's kind of unavoidable. All right. So what we got?
Do V2 prime as V3 for that last.
Did I just do the wrong one? Oh, V2 prime. Yeah, it's supposed to be 1. Thank you. Yeah, that'll happen. Thank you, thank you. I appreciate the immediate pushback. Very, very welcomed. I'm not Trump. Let's see here. Let's see here. 1, 1, minus 2, 8. See here. 3 halves. Where we got? 3 halves? Yeah, 3 halves. Let me try to do the arithmetic there. So minus, that's going to work out to 9 halves. 3 halves, 3 halves. Wait a minute, that's going to be a minus. Oh, I did the minus outside, so minus 3 halves. That's where you get into trouble, if you kind of go halfway on a sign convention. 9 halves. That's plus 1 half, 3 halves, 3 halves. And then minus 1 half. All right. What we got here? Wheel. 1 minus 9 halves plus 1 half. Minus 2 minus 3 halves plus 3 halves, and of course, oh, come on, good grief. All right, you know what? Let's stick a fork in this thing. Like, you know, let us not write down this step. Let's just do this step. Writing is not helping. 1, this is what? This is minus 9 halves. So we've got a minus 8 halves, which is minus 4. I believe I have a minus 3. The 3 and the 3 halves, these guys would be canceling. I got a 1. Again, oh, plus. So plus 3. So I get a 1. And then this looks like a net of minus 10 halves, also known as minus 5, so I got a 3. Is that perpendicular to the previous two, right? So minus 3 plus 3 plus 3 minus 3. Good. The dot product of this with V2 prime is 0. Good sign. The dot product of, so I got a minus 9 plus 3, minus 3 plus 9. Yeah, 0. Yay. All right. So there we go. My S prime, which we could write of, I'm not going to write it again, but V1 prime, V2 prime, V3 prime is orthogonal, right? Then how do I write this as a orthonormal set? Maybe we can use prime prime for orthonormal, right? So let's say S prime prime orthonormal construct by normalizing vectors in S prime. So like S prime prime, so like what's the length of V prime? Well, it's V1 prime. It's 1 over the square root of 20, yeah? And then we had 3, 1, minus 1, 3. All right. And V2 prime, same song and dance, 1 over the square root of 20. Different vector, of course, but same normalization. 1, 3, 3, minus 1. All right. And then finally, again, square root 1 over square root of 20. They don't always have to be the same. That's just a quirk of this example. 1, 1, 3, right? So it turns out there's something very interesting here called the QR decomposition. All right, there's something called the QR decomposition theorem. Given A with linearly independent columns, we can do Graham-Schmidt on the columns of A and find orthogonal matrix Q and upper triangular matrix R such that A is equal to QR. And this is called the QR decomposition. All right. Now we can use the calculation we've already done today to set it up for the matrix, which I would usually just call the matrix of S in here. So like, now the R is perhaps not obvious, I guess, but and perhaps the Q isn't either. Let's see here. But let's see here. The A I have in mind. What is it? Oh, so the A I have in mind here is the 3, 1, minus 1, 3. And minus 5, 1, 5, minus 7. I've already forgotten. What did I say?
Minus 5, 1, 5, minus 7.
Thank you. What's the third?
1, 1, minus 2, 8.
All right, cool. So it turns out we can use this example that we just did to find a QR decomposition for this matrix. All right? So, yeah. I guess we'll pick up there next time. So, thanks, guys. There's an example of the QR decomposition at the very end of my notes on like page 304. There's just one example at the moment. So if you're looking for one, that's where it is.